Hello, my name is Geoffrey, and I'm really excited to be here to present Habitat, a runtime-based computational performance predictor for deep neural network training. This is joint work with Yubo, Pavel, and Gennady, who is my advisor at the University of Toronto. Okay, let's get started. Today, deep learning users have a vast array of GPU options available to them for training, each with a different cost and performance. And this presents a new problem. Which GPU should they use for training their models? Well, one way to make an informed choice is to predict the performance you'll get when training your model on a given GPU. And we make the observation that the computation during deep neural network training is highly repetitive. And so this means that it's actually feasible to predict the performance of a training process. We just need to predict the execution time of a single training iteration. And so the key idea in our work is to use an existing GPU to help make these predictions. We use a combination of wave scaling, which is a new technique based on hardware ratios, and pre-trained multilayer perceptrons. We implement these techniques into a tool called Habitat, which is open source and supports PyTorch. And we show two case studies where Habitat's predictions help users choose the right GPU for their use case. Deep neural networks have seen incredible success across many machine learning tasks, which has led them to become widely used throughout both academia and industry. But the problem is that they're often computationally expensive to train. And this has led to a significant investment in bringing hardware acceleration to deep neural network training. And today, there's a vast array of GPU options available, both for workstations and servers in the cloud. But even beyond GPUs, there are also TPUs that span several versions, as well as other emerging accelerators, such as the Cerebra's wafer scale engine, the Habana Gaudi, and the recently announced AWS Trainium chip. Having all these options empowers users, but also leads to the question of which accelerator should a user use when training their models. In this work, we start by focusing on answering this question for GPUs. And that's because they are commonly used in deep learning and are readily available for both purchase and rent. But even when just considering GPUs, users are often faced with a paradox of choice. For example, a common scenario is having to choose between GPUs available in different tiers. A user could have a GPU available in their personal workstation, such as the 3090, another GPU available to them in their institution's private cluster, like the P100, and also the option to rent GPUs in the cloud, like the V100 and T4. But when choosing, users might want to optimize for different factors, such as performance, or cost, or both. And the problem is that there is no one-size-fits-all choice. The correct choice depends on what the user is optimizing for. Okay, so at this point you might be wondering, okay, well, why not just measure performance directly instead of predicting? Well, to do that, you actually need to get access to the GPUs you're considering, which often costs money. Ideally, you would want to make this decision before spending that money. And on top of that, making measurements gets very tedious when you need to repeat the measurements for many different models and GPUs. Okay, then why not use existing benchmarking results? Well, they are typically only available for a few popular models, such as ResNet and BERT, and for cloud GPUs, like the V100, A100, and T4. If you're developing a new custom model, which is often the case when you're doing deep learning research, you will not have any results to rely on. Okay, then what about using heuristics, like making a back-of-the-envelope calculation to estimate performance? Well, they don't always work. For example, we measured DCGAN's training iteration execution time on the T4. And then we multiplied that measurement by the ratio between the T4's peak flops and that of 5 other GPUs, just to estimate their performance. But it turns out that this simple heuristic works poorly. It leads to prediction errors of at least 43%. And so really, to get accurate predictions, we need to take a different approach. So in our work, we make 3 key observations that we leverage to make these accurate predictions. First, deep learning users often already have an existing GPU available to them. For example, they might already have a GPU in their workstation that they use for development. And second, deep neural network training computation really is a highly repetitive process with short training iterations. So this means that predicting the performance of a training process just reduces down to predicting the execution time of one training iteration. So we can leverage a user's existing GPU to predict a deep neural network's training performance on other GPUs. And this is the central technique that we develop in this work. And so we built Habitat, a computational performance predictor for deep neural network training. At a high level, Habitat's workflow has 3 steps. First, it measures the execution time of each operation that runs in a training iteration, along with some other runtime metadata. Then, using those measurements, it applies either wave scaling or pre-trained multilayer perceptrons to each of the operations to predict the execution time of the operation on a different GPU. Finally, it combines these measurements together to arrive at a single end-to-end iteration execution time prediction for the other GPU. This can then be used to calculate throughput and cost-normalized throughput. Habitat itself is implemented as a Python library that currently supports PyTorch, and it is open source. So now let's dive into how Habitat makes its predictions. First, I'm going to present some background about a GPU's execution model, which is important to be able to understand how Habitat works. Deep neural network operations, when executed on a GPU, are composed of one or more GPU kernels. You can think of a kernel like a procedure or function that runs on the GPU. Kernels themselves are divided into thread blocks, which are units of work that run the same code but operate on different data. GPUs consist of a number of streaming multiprocessors, or SMs, which run a finite number of these thread blocks concurrently. This is how the GPU achieves parallelism when executing a kernel. So the thread blocks are round-robin scheduled onto the SMs. Because the SMs only run a finite number of these thread blocks concurrently, the scheduling model results in waves of thread blocks that execute on the GPU. In this example, running that kernel leads to 2 thread block waves. And this leads us to Habitat's key prediction technique, which we call wave scaling. Wave scaling works on individual GPU kernels. Given a kernel's execution time on one GPU, for example 200 microseconds here, wave scaling predicts the kernel's execution time on a different GPU without actually running it on that other GPU. And it does this using the 2 GPUs' hardware specifications. Let's walk through an example. In line with its name, wave scaling works with thread block waves. So first, it computes how long a wave takes by dividing the kernel's execution time by the number of waves. Computing the number of waves for a GPU is straightforward, and Habitat does this using the CUDA toolkit. So in our example, the kernel takes 2 waves to complete on GPU A, and this is because only 4 of its 8 thread blocks run concurrently on the GPU. So a wave would take 100 microseconds. And now to predict the wave's execution time on GPU B, wave scaling scales this 100 microseconds using 3 factors. First, the memory bandwidth ratio between the 2 GPUs. Second, the number of thread blocks in the waves, in other words, the size of the wave on each GPU. And third, the clock frequency ratio between the 2 GPUs. So here's the intuition. Suppose the kernel is memory bandwidth bound. If the memory bandwidth on GPU B is, say, 2 times higher than GPU A, then the wave's execution time should decrease by up to 2 times. And this is because if there's twice as much bandwidth available to serve the memory requests, then you'll be able to complete them up to 2 times faster. Similarly, if the memory bandwidth on GPU B was lower than GPU A, then the opposite would happen. Okay, next, wave scaling takes into account the size of the wave. Again, suppose the kernel is memory bandwidth bound. If a single wave on GPU B is twice as large as a wave on GPU A, and the GPU's memory bandwidths are the same, then the wave should take 2 times longer on GPU B. And this is because having more thread blocks means more memory requests are going to be made in the same wave. And if the memory bandwidth is the same between the GPUs, then it'll take up to 2 times longer to serve all those requests. And just like before, this effect is analogous if the wave was smaller on GPU B instead. In this example, I'm showing you a wave of the same size. Finally, what if the kernel is not memory bandwidth bound, but compute bound instead? Then the clock frequency plays a larger role. If the clock frequency on GPU B is 2 times higher than on GPU A, then we would expect the wave to run twice as fast because it is compute bound. Okay, now let's complete our example. So suppose the kernel is memory bandwidth bound and that GPU B's memory bandwidth is 2 times higher than GPU A. So using the bandwidth alone, we would expect the wave on GPU B to run twice as fast. But we also need to keep in mind that GPU B's wave will be twice as large because it has more SMs. Notice here that there are 8 thread blocks in a wave on GPU B. So taking into account the bandwidth and wave size, wave scaling would predict that a wave on GPU B takes the same amount of time as on GPU A. Finally, we need to go back to the kernel execution time. So notice that GPU B can process all of the kernel's thread blocks in a single wave, and that's because the wave is larger. Therefore, overall, wave scaling would also predict that the kernel itself will run in 100 microseconds on GPU B, which is 2 times faster compared to GPU A. We describe wave scaling more formally in our paper, and I encourage you to check it out for more details. Now there's one last wrinkle. Wave scaling works when the same kernel is used on both GPUs. But there are a few deep neural network operations that use different kernels on different GPUs for performance reasons, and we call these operations kernel-varying in the paper. Habitat makes predictions for these operations using pre-trained multilayer perceptrons, which you can read more about in our paper. Okay, now for our evaluation. We had 2 questions we wanted to answer when we set out to do our evaluation. First, of course, is how accurate are Habitat's predictions? Second, we wanted to see if Habitat's predictions would lead users to make the correct decisions based on their needs. So we used 6 GPUs in our evaluation, and they span 3 generations, Pascal, Volta, and Turing. And they consist of both workstation GPUs and server GPUs. And second, we evaluated on 5 models. This includes ResNet 50 and Inception v3, which are convolutional neural networks for image classification, GNMT, which is a recurrent neural network for machine translation, the Transformer, which is an attention-based model, but also for machine translation, and DCGAN, which is a generative adversarial model for image generation. We ran all our experiments on PyTorch 1.4, and if you want to learn more about our methodology, please see our paper. So to evaluate Habitat's accuracy, we used it to predict the iteration execution time of each of the GPUs and models that I mentioned on the previous slide. So here's a concrete example of the experiments we ran. Recall that Habitat needs an existing GPU for its profiling pass. So here we took ResNet 50 with a batch size of 32 and ran it on the 2070, which here we're calling the origin GPU. Then we used Habitat to predict the iteration execution time on the V100, and here that's the destination GPU. So in this setup, Habitat's prediction error was 1.9%. We repeated this experiment for all 5 models across 3 batch sizes and for all 30 possible pairs of the origin and destination GPUs. And among all these configurations, Habitat's average error was 11.8%. So we conclude that Habitat makes accurate iteration execution time predictions. But next, we wanted to see if Habitat's predictions can actually help a user make the correct decision for their specific situation. And for this, we examined 2 case studies. So suppose a user wants to train GNMT, and they already have a P4000. They want to figure out which cloud GPU they should use, if any. Well, they can use Habitat with their P4000 to predict the training throughput on the V100, T4, and P100. So on this graph, I'm showing the training throughput of each of these GPUs normalized to the P4000 for 3 different batch sizes. Above each bar, the percentage is Habitat's prediction error. So a normalized throughput above 1 means the GPU will have a better training throughput compared to the P4000. Notice that despite any prediction errors, Habitat correctly predicts that the V100 is the best choice for performance, followed by the P100. The T4, on the other hand, only offers marginal improvements over the P4000. But what if we take cost into account? On this next graph, the y-axis is now the cost-normalized training throughput, and we normalize by each GPU's hourly rental rate on Google Cloud. Here, notice that the T4 is now the best option. And again, despite any prediction errors, Habitat correctly predicts the relative ordering among these GPUs. So ultimately, the user's best choice depends on their needs. If they want to train their model as fast as possible, the V100 is their best choice. But if they're not critically constrained by time and want to save money, renting the T4 or just sticking with the P4000 is the best choice. And this is because the T4 only offers marginal improvements over the P4000, which the user already has. Okay, so from that case study, a natural thing to wonder is, should we just always select the best GPU available if we want performance? For example, suppose a user wants to train DCGAN and they have a 2080 Ti, and they want to know if it's worth using the V100 because they think it's the best GPU available for them. Well, they can use Habitat to make a prediction. On this graph, I'm showing each of the 5 other GPUs' DCGAN training throughput, normalized to the 2080 Ti. Again, the percentages are Habitat's prediction errors, and a normalized throughput above 1 means the GPU does better than the 2080 Ti. These results show that the V100 only offers a marginal improvement over the 2080 Ti, which Habitat correctly predicts. So it would not be worth it for this user to rent the V100 in this case. We have additional details in our paper that I didn't get a chance to cover in this talk, and I'd encourage you to check it out, where you can see additional results and read an extensive discussion section about how Habitat can be extended to other training setups and other hardware. To conclude, I wanted to highlight the key takeaways that I hope you got from this talk. First, deep neural network training computation is special because it is repetitive, and this enables new analysis opportunities. Habitat leverages this repetitiveness to use runtime-based information to make its iteration execution time predictions. And in the case studies we showed, despite any prediction errors, Habitat correctly predicts the relative ordering among the GPUs that were being considered, and this allows users to make the correct decision for their needs. And finally, the hardware landscape for deep neural network training is really growing. Users will need help choosing the right accelerator effectively, and Habitat is one tool that can help. Habitat is open source, it currently supports PyTorch, and it is available on GitHub. And thank you for listening to our talk.